So graphs. Graphs is another data structure that most of you have seen, right? Anybody who's not seen graphs before? Not seen graphs? Graphs. Oh, good. Then we'll need to cover it in more detail. Okay. But a few who have never seen graphs. So what is graph? Those who have seen it, who can tell me what is graph? What is a graph? With regards to data structures, what's a graph?
Non-linear.
So what?
Non-linear data structure.
Non-linear data structure, sure. Anyone knows the precise definition of a graph? It's pretty simple.
Collection of nodes and edges.
Sure. That is correct. But graph actually is a pair. Understand it simply. A graph, data structure, graph is a pair. A pair is always of two things. What are those two things? Sets of vertices and sets of edges. So it's a pair of two sets. You got a set of, well, actually, you write it like this, V and E, where V is a set of vertices and E is a set of edges. So if you have a graph, so let's just draw a graph for 1, 3, and then 2, then maybe 5. So let's get a 5 and 2 as well. What will be the representation of this graph? In mathematics, it is same V and E, where V is 1, 2, 3, 4, and 5, no order. How do you know there's no order? Because it's not directed, there's no order. Because it's a set. Irrespective whether directed or not directed, there is no order of vertices. Is there an order in edges? If it's directed? You guys are missing one important thing. You're thinking good, but you're missing an important point. We'll make it direct in 1 second. Now, tell me the edges. What will go in this set? Now, an edge is a pair of vertices that the edge connects, and so it will be 1, 4, 1, 3, 1, 2, 4, 3, 3, 5, and 5, 2. Right? Now, when I say is there an order among edges, see, this is a set. You can write these in any order you want. In a directed graph, 5, 2 is different from 2, 5. In an undirected graph, 5, 2 is same as 2, 5. So there is a direction in the pair, in this individual edge, individual pair. But you can write them in any order because it's a set. A set never has order among its elements. And so that's what a graph is. What good is this? What good is this? How does, it's a data structure. Remember we talked about data structure? Provides structure to data. What structure does it provide to the data? Or what kind of data is this good for?
Can implement paths. Provide paths.
Links. Provide paths. Sure. So many of you have done graphs before. When we talked about stack, what structure does stack provide to data?
Access of data.
The last in, first out. So whenever you have a set of data where there is a linear ordering, A comes after B comes after A, C comes after B, D comes after C, in that order you can create a stack. You have Q, again there is an order, a different order, first in, first out, you do it. For a tree, what kind of relation do you have in a tree? A parent-child relationship. Whenever you have a data where you have one data spawning other data, and those are other data pieces spawning other data pieces, you know that that kind of parent-child relationship can be captured easily with a tree. What?
Path between
Cyclic path. When you have connections between data sets, when the links are connections.
When you have connections between data sets. What kind of connections?
Any can be traversed from one.
So do understand this path and all came about after. Those are bonuses of having data represented as a graph. Say graphs have never been discovered. What kind of data set would you see that would prompt you to say, oh, no, I need a different data structure from what I've seen so far? If I give you names of all the students in this room, would you create a graph with it? I give you just the names of all the students. Can you create a graph with it?
Yeah.
I only have names for students. I can create each name or each student has as a vertex. They're all disconnected, but it's a graph. Any data can be represented by a graph. Whether it will be useful or not, a different story. It can be represented by a graph. Now, how do we make it useful? So say I give you names of 20 students in the class. Just make graphs. You have a question?
I was just saying that by defining the relationship in the
Correct. So what kind of relation? Definitely. So you need to have some relation between the thing. Like in tree, we have the parent-child relation. And do you know tree is also a graph? Is that true?
Yes.
Tree is an acyclic graph, right? And so a directed acyclic graph. We don't draw directions in a tree, but a tree edge always goes from the parent to the child. So, what was I saying? Yeah, so I give you names of students, 20 students. You draw 20 things. And now I give you, say, their age information. Now do you make it a graph? For example, say I got, say, J for John, M for Mary. Now I'm not making the connections yet. And say you have A, again I'm making connections. So you got A, you got B, all these are say names. And now I tell you that J is 26-year-old, B is 29, and M is 26 again, and A is 24. Can you now create a graph? You can define rules based on which you can create a graph. Right, you have to define rules based on which. So now, would you do this? Would you say, okay, 26 is one number, 24 is another number, and now J connects to 26, M connects to 26, A connects to 24, and B connects to 29? Would you do that? No, don't do that. See, that's why there is these fundamental things that you have to understand. These are information about these data points that you have, right? They are properties of those. So it's more like you still have the same nodes, but you got B and then 29 here. You don't have 24, you got like A and 24, right? You got M 26, you got J 26. These are information about those things. These nodes have to be similar in nature, and you need to make connections. So whenever you have these data sets, you always have keys that identify each piece of data from the other data, right? And these age is not that key. The names are the key. Now you have to connect the keys. How do you form a relation? For example, if I give you their birth month, and now you can relate people, all the people in this class, by their birth month. So you get a cluster for January. Every people who are born in January, you got a cluster. If you all people born in February, you got a cluster, and so on. So you have to define the relationship. When you have the relationship, you can create a graph. How is graph useful?
We could have done the same with the age also.
We could have done the same with age.
So now, yes, we can. So for example, I can connect these two because they have the same age. And then the relationship is. But what I'm saying is you're going to create a node 26 and connect with that. The relationships are captured in the edges. Vertices are independent entities. And relationships are captured through the edges. And so that relationship you will have to define that, okay, these two are connected because they have the same age, It's the same edge, same age, right? And so, make sense? So again, graph is the most general data structure that you will see. Any kind of data can be represented by graph if you do it correctly, and you can use it. Now, what have you, so people who have never seen graph, this is the definition of a graph. It's a pair of two sets of vertices, sets of edges, and you link them. For example, you got a bunch of cities, you got roads connecting those cities, you have length for those roads, you can create a graph. And connecting all the connecting cities or the roads can be the edges. The length of the roads can be the weights on those edges. Now, do all graphs have to have, all edges in the graph have to have weights? No. It's called a weighted graph when you have weights on the edges. Now, in a graph, can you have a node connecting to itself? Yes. Sure. There are graphs that do not allow that. So you can have, graph is very general, you can have a bunch of things. Now, with this connectivity that you have, you can create a path to go from, say you want to go from 3 to 2. How many different ways can you do it? You can go like this, you can go like this, you can go like this. Excuse me. So all those can be analyzed, can be done. Again, the idea is, it's a very general data structure. Now we'll look into graph traversals and things you can do with the graph. But before we do that, we would look into how to represent a graph. This is a mathematical representation. How do we do a programmatic representation of a graph? Okay, we'll talk about that in a second. So quickly, graph is a pair of two sets, vertices, set of vertices, set of edges. Very simple data structure. What does this mean? Whenever you have a set, what does the two lines around the set mean? The number of elements in the set, or the cardinality of the set, or the size of the set, right? So it says the size of the set E is equal to order big O of V squared. Does that look correct?
Yeah, that's on.
What's the maximum number of edges you can have in, say, can you have n square edges in an n node graph? The question is, so this is a 5 vertex graph. Can you have 25 edges in this graph?
No.
Yes. Yes, there can be self loops if you allow. You can have. So 3 can have how many maximum edges? One with each one of these other nodes and one with itself. So each node can have 5 edges. There are 5 nodes. You got 25 edges. If you do not allow self loops, how many edges can you have?
N into N minus 1.
N into N minus 1 by 2. Not N minus 1. Right? You can have more than N minus 1 edge in this itself, right? So, why this? Quickly. NC2, exactly. You got N nodes. You choose 2 from it, so NC2 will give you N into N minus 1 by 2. NC2 actually is N factorial divided by N minus 2 factorial, 2 factorial times 2 factorial. It gives you N into N minus 1 into N minus 2 factorial. That cancels the base N minus 2 factorial, and then you got 2 factorial, which is 2. So N into N minus 1 by 2. That's what you get. But in both cases, it's big O of N square if N is the number of nodes you have, or V square if V is the number of vertices you have. What's a connected graph? A connected graph has a path from every vertex to every other. Is this a connected graph? No? Yes, if I remove these 2 edges. Yes. Connected graph? More clear. Yes. Anybody who thinks no? It's okay to say no. Yes, the confusion that you may have, and that I'm trying to clarify, it does not say a connected graph has an edge from every vertex to every vertex. It says it has a path from every vertex to every vertex. So you basically, if you can start from 3 and go to every vertex, then it's pretty much you have a connected graph. How? Don't we have to check for the others? What I'm saying is if you start from 3 and you can go to all the vertices, then it's connected.
Yes.
Don't I have to check from 1 and 2 and 5? Why not? Because I can go back to 3 and then connect to whichever vertex I want to. Exactly. So, now in an undirected graph, the edge UV is same as VU. There is no direction, but no self loops. Won't make sense. In a directed graph, an edge UV goes from vertex U to V, and so you usually put an arrow in a directed graph. Okay? Now in a directed graph, you don't have a choice of putting a few arrows and few not. All edges should have arrows. So if you have bidirection, you want to make 2 edges. A weighted graph associates weight with either of the edges or the vertices. Mostly edges. Very few times you'll see, rarely vertices, but edges carry weight. That's the weight of the relationship between the 2 nodes. Right? That was supposed to be a joke, it didn't work. Okay. Now, remember, nodes are related. So in a graph, weight is the weight of the relationship. Okay. Now, so a road map, edges might be weighted with distance that you have. A multi-graph allows multiple edges between the same vertices. So you can have this, and then you can have this. Multiple edges between, not multiple paths. Multiple edges between 2 vertices. How can that be useful? There are some situations. One example here is if you're drawing, or if you're making a call graph in a program, and you have a function, say A, that calls function B 3 times in the body, then you will have A connected to B at 3 different points, right? And so, can be useful. Now, when the number of edges is close to B squared, the number of vertices squared, then it's a dense graph. When it is close to the number of vertices, then it's a sparse graph. Usually graphs are between, not that dense, not that sparse. But why do we have to make this distinction? Because if we know beforehand that the graph is dense or sparse, we can use different data structures for efficiency purposes to represent those graphs. Okay? So, how would you programmatically represent this graph? What known data structure would you use to represent this? So this is what you have. So
2D array we can use.
So one answer I got is that you can use a 2-dimensional array to represent your graph. Do remember that you have to represent the vertices, you have to represent the edges. Then only you represent the whole graph, right? And so how can you represent this with a 2-dimensional array?
Array of point vertices.
Whenever there is a connection, you can just put a value of 1 or 0.
So first tell me, so how big a 2D array would you need for that graph?
5 cross 5.
A 5 by 5 2D array, right? And so, let me not. Okay. Now, how do you represent that graph? Raise your hand if you want to give an answer.
If there's a connection and if there's a weight, so suppose there's a connection between edge number 1, vertex number 1 and 2, you put the number there, and if there's no connection, you can put 0.
Sure. So say let's not have weight at this point. This is the graph. How would you do it?
So you write 1, 2,
So 1, 2, 3, 4, 5.
Right.
If there's a connection, write 1.
You write 1, 2, 3, 4, 5, the nodes, or 0, 1, 2, doesn't matter. 3, 4, and 5. You got the same vertices. So this represents, the indices represent the vertices. And how do you represent the edges? If there is a connection between, say, 1 and 2, is there one? Yes. 1 and 2. So you put a 1 in there. Is there a connection between 1 and 1? No, so you put a 0 in there. So all these are zeros because they are now self loops. And then, is there a connection between 2 and 1? Yes, and so on. So, that's how you would represent this graph. Is this the best way to do it? No? Yes?
Linked list is the graph. Linked list can be used.
We can reduce half of it. So in an undirected graph, what you have on the top side is the mirror image of what you have on the bottom side. So you can use half of it. But how do you use half of it? What data structure do you use to use half of it? None. If you have to use an array, you do it, and by n. You don't have a triangular array, right? So
what in non-directed graph we can consider the half triangle.
in the directed graph we cannot. So that's what I mentioned. So in non-directed graph or undirected graph we can do this. In a directed graph, both sides are used. Sure. Now, is this absolutely useless, or in some situations this is good? If the graph is dense, it is good. If the graph is sparse, it's not good. You will have a large, like if you want to represent the graph that would represent every connections on Facebook. Is that a dense graph or a sparse graph? It's a very, very sparse graph, right? Because you got so many people, but only few are connected. So such will take a very large space and not much good. So what's the other way to do it? Again, I'm going a little slow on this because many of you said you have never seen graphs before. If you have questions, then let me know.
Can you do a hash map of all of the vertices and then a list of all the other vertices that connect?
So can you use hash map? It's a very good point, but let's analyze this point quickly. Can you use hash map when you have relations between data pieces? If you have a set of data points and you want to store them efficiently, you use hash map. Right? Now here, how would a hash map represent the connection between 3 and 4?
It'll be the key 3, and then you would have an array or a list of 4 or 5.
So you're saying there's a key back. Oh, okay.
Yeah, the key is the vertex.
Right. So I see what you're saying. So usually, sure, that's the other representation, but not as a hash map, but it's more like the array of linked lists, which is very similar to what you're thinking. Absolutely. See, a hash map would require you to have a hashing function, right? Or you're thinking of key value pairs,
Yeah.
and where the values are way more, meaning you can have like 3, the value, you are thinking of 3, and then the value to it is a list of all the nodes that it has.
Yeah.
Sure, then yeah. If that's what you're thinking, then 4, 1, 2, 5, and so on. Now, this is what we call an adjacency list. So do understand that in both these representations, I'm going to show you this in a second. So you got 3, then you got 4, and you capture all the things that are connected to 4. So you got 3, 1, and then you got 5, and all the nodes that are connected to 5. You got 3 and 2, and then so on.
3 doesn't, is 3 and 2? 3 doesn't have to be.
No, I'm talking about 5. 5 has an edge with 2 and first one. Or 3 doesn't connect to 2. So that's good. So 3 maps to 5, so on. So yeah, so you will have 5 lists here for 5 vertices, and you contain the information about what they are adjacent to. In here also we are storing the adjacency values. Is 2 adjacent to 1? True. If 3 adjacent to 1, say false, if that was the case, and so on. So we are storing 0, 1 values that represent whether they are connected or not. And so these are 2 well-known representations for a graph. This one is very good when it's dense, as well as when it's directed and dense. It helps more. This is very useful when it's sparse. Yes. So An adjacency matrix is represent the graph as an n by n matrix, and the value that you have at aij is the name of your matrix is 1 if edge ij is present in the set of edges. If 0 if edge ij is not present in the set of edges. And so, what would be the adjacency matrix for this? Pretty easy. You can just do this. Now, instead of storing 0 and 1, you can store the weights if you want, and those weights can represent that they are connected. If they are not connected, you can store, say, a -1 in there, rather than storing a 0, because 0 could be a valid value, valid weight that you have for the two nodes connection. Questions so far? All good? Okay. So this is a very yes.
So the adjacency list, that the array of lists that was suggested, won't that also have redundant information about undirected graph?
Yes, it will. So here it is being duplicated, like you're saying. 3 is connected to 5, and then 5 is connected to 3. So it is double in this case. It is double in this case. But the difference is that the number of nodes you will have, the number of nodes, number of things you will have is equal to the number of edges times 2 in here, versus this one, if you have like 1,000 vertices, it will be a 1,000 times 1,000 array size with lots of zeros in it. But there is no 0 getting stored here. Do you see the difference? So we'll do the analysis very quickly here. But you're right that for directed, they both, well, for directed, this is good. For undirected, this will have double the information than that. One easy way to take care of that, anyone know?
Not store if it's already stored.
Take a flag.
Not store if it's already stored? What does that mean?
Like if 3 and 5 is already stored, you don't need to store something.
Sure, but how do you check for that? So one easy way to do that is, even though in an undirected graph you don't have directions, as long as you know that, you can just for storing purposes, you can keep a direction. What that means is, now there are disadvantages to that approach. But if memory is really an issue for you, you can always say that for storing purposes, we are going to store, say, this connection from 3 to 4 will only be stored in the smaller ones or the larger ones list. So 3 will have the connection 3 to 4, but 4 will not have the connection 4 to 3. But now, while traversing this graph, if you are at 4 and you want to go to 3, you will not be able to. So there are advantages, disadvantages to that, and so it is stored like this. Such problem does not occur. If there was a way to store this as half triangle, half of the square, the triangle, such problem would not arise, because you can switch the row and this. In this case also, if you are at 3, and you want to know if you are connected to 4 or not, or where all can you go from 3, you will not have the information if you're connected to 4 or not. So in both cases, to save that space, you will have to do more in your search, in your exploration, than just directly going to it. Right? So, yes.
How would you represent the weighted graph in the other projections?
So we'll look at it. We'll look. We can again, these things, we can add weights to anywhere. In here you can have direct values, but here you can keep them weights in as a piece of information stored. Again, do remember, weights are not the key. Weights are additional information. Remember the thing that I was telling you when you have a name and age? The name is the key. Age is just an additional information for that thing. Here, the key for an edge is the connection between 3 and 4. Weight is just an additional information. You can store it in this node. That node that you make will have 2 pieces of information rather than 1. One is the key and one is the value. That's a very general approach that I'm telling you, that whenever you have keys and information associated with the keys, all those additional information can be stored in that node if you want to, in general. Now, adjacency matrix, how much storage does the adjacency matrix require? Matrix, V square, Simple, order of V square. You got that thing? But let's look at this. What is the minimum amount of storage needed by an adjacency matrix representation for an undirected graph with 4 vertices? Now this is in terms of bits and bytes. If there was a way to optimize it, see the upper portion is the asymptotic requirement, order of V squared. Now if I got 4 vertices and I'm storing only one side of it, then I just need 1, 2, 3, 4, 5, and 6. These are the only things that I need to store. And because I'm storing zeros and 1, I just need 6 bits to store that. That's the minimum amount of information. So when you practically do it, you may not need that much space. When we deal with sparse matrices, we do make use of bits in a byte to represent the whole matrix. And so undirected graph matrix is symmetric, no self loops, don't need diagonal. So this is just to give you an idea of that we don't really, if you have to do a production level thing, you don't really store it as full nodes. You can even, the adjacency information can be stored in 1 bit between the 2 nodes. Now, adjacency matrix is a dense representation, usually too much storage for larger graphs, but can be very efficient for smaller graphs. Why is it efficient?
Faster access.
Faster access. Why faster access? Because it's an array. It's a random access. You directly go to it, right? And so, most large interesting graphs are sparse. So adjacency matrix may not be that much of a deal. Planar graphs in which no edges cross have E equals order V. So for this reason, the adjacency list is often a more appropriate representation. Right? Planar graph is a graph that you can draw on a plane. No edges cross. You might have seen this in your childhood days, drawing this, right, without lifting your pen and crossing or something. And so those are, here the edges cross, right? It's very hard to draw this. It's actually possible to draw this. So this edge, I think you can draw out. Are the edges crossing in here? Anyway, don't worry about it. But point is that the point is that the interesting graphs are sparse, and so adjacency matrix may not be the best representation. What's an adjacency list? Like mentioned, every vertex will have a corresponding list associated of the vertices that it is adjacent to. And so for this graph, this is the adjacency list. Now this is a directed graph, and that's why you see it like this. Now, if you, this is where starting from that node, so starting from 1, where all can you go? You can go to 2 and 3. So 1 goes to 2 and 3. But you can also keep the reverse list, where this is like a doubly linked list kind of a thing, where you can also maintain the same adjacency list for edges coming into a vertex. So in that case, for the list of 2, you will have 1. In the list of 2 now, you have 3, because from 2 to 3 there is an edge. But you can maintain the reverse as well. And for the same advantages that you have between a doubly versus singly. How much storage do you need for adjacency list? The degree of a vertex V is equal to number of incident edges. So this is the definition for a degree of vertex of a vertex. So what's the degree of 2? 1 incident coming into it. What's the degree of 3? 3, and so on. So directed graphs have in degree and out degree. Undirected graphs just have the number of connections that you have. Now for directed graphs, the number of items in adjacency list is the sum of out degrees, because that's what you maintain in the directed graph, right? The sum of all the out degrees that you have, and is equal to E. And so it takes V and E number of storage. So V plus E, order of V plus E. Is it better than order of V squared? What is usually smaller? The number of vertices, number of edges? vertices is smaller. So V square versus V plus E. V plus is still better because it's not V times E. It's V plus E, and so better. Now, that's why this works so much better for a sparse graph. For undirected, 2 times E, and so still it is the order, or basically theta, of V plus E. So in adjacency list, irrespective of whether it's directed or undirected, it takes theta V plus E. Storage. Now, we did look at 2 mechanisms to store a graph. That's why we were doing analysis of how much space it needs. Now we want to do some operations on a graph. And then we will analyze which one is better based on the terms of operation. Given a graph G equals V, comma E directed or undirected, we want to methodically explore every vertex and every edge. How can we do that? Again, people have seen graphs before, will have the answer for that. People have not seen graphs before. Think about how to explore the graph. Does a graph have a starting node? Like a tree? Tree has a root node. You can start exploration from there. Does a graph have a root node? No. But you can start from any node. Right? How do you explore a graph? In a tree, you just go from top to bottom. It's all good. In a graph, what? One into the other. But is there any issue with that? So there are no. Again, don't give me the details of the algorithm. At a very high level, do you see the issues for exploring, related to exploring a graph? You start from 3, you go to 4. Now what do? You have a choice of continuing from 4 to something, but from 3 you went to 4. There are other things to explore from 3. So do you explore all the things that you can explore from 3 first? Or do you go to 1 and then explore further and further and further? Right? And that gives rise to 2 very famous graph exploration algorithms. The depth first search and the breadth first search. They both have their advantages and disadvantages. That's why we have 2. Right? One is good enough and nothing is no better than the other. We will not talk about 2. So a breadth first search is you start from a node and you explore all the adjacent nodes. Then what do?
Go to the next.
Next from which one? Because I got to 4, 1 and 5 at the same time.
First to the left.
All of them.
We can maintain a stack or maybe just put in the notes.
Right. No, we can. Not a stack.
Q.
A queue. So I mark one node as my start node, and I have a queue. So the one that comes in first in the queue will be explored first. And so from 3, which one do I go to? 4, 1, or 5? It doesn't matter. Is it guided by something? It's guided by something. Order that is stored in here, right? And so if you're using that versus this, there's some guidance you will have, but yeah, it doesn't matter which one you go to first. So first you will put your start node in the queue. Then you take this node out 3 and you explore the adjacent nodes too from 3, and so you got 4, 1, and 5. Now you take out the next one out. So 4, you got 4 out, and now you explore everything that you can go to 4. So you got 1 and nothing else, right? But 1 has already been put in there. We'll maintain that information somehow that 1 has been put in there. You're not going to put again. So 4 has been explored. Now you take out 1 from the queue and you explore 1. You go to 3 and 2. 3 has already been explored. So you put 2 in there. And then you take 5 out and so on.
So if it's search, why don't we just look at the list of set of vertices that we have? Why do we have to search using vertices, or using edges that we have?
So it's not a search. It can be used for a search. It's more of an exploration. So a traversal, rather. The idea is to go to all the nodes and cover as many edges. Now, what do you mean by a search? So what did you have in your mind when you said if it's a search, why can't we do this?
Yeah, simple search when you're looking for an item in the whole graph.
In the whole graph, sure. So in the graph, the items are stored the way you are seeing here and here. You can go to them directly. So we never do a search for a vertex in a graph. Oh, we are almost out of time. Okay, let me quickly explain this thought. We never do a search for a vertex on a graph that's readily available. We never do a search for an edge on a graph. We can check if an edge is present or not if we have two vertices, and that also is readily available. So we don't do those things in a graph. But still, the graph can give us a lot of information. Any quick question? Almost out of time. Alright guys, good luck for the exam on Thursday.
Is it 1 hour or 1 hour 15 minutes?